I work for a particular, it's a distributed company. We make a product called Service Bus, which is a messaging framework. And I'm not going to talk about the product, but messaging in general, as I figured it applies to all things microservices. I prepared this talk for a Swiss user group that invited me in September. And the one funny thing that happened there in in Lucerne when I was there, was that before my talk, they excused me and they said that they are going to discuss unit test frameworks for 20 minutes in Swiss Dutch, not even regular German, so that I could not understand anything. So if you want to just discuss anything in Gaelic, feel free. I won't feel offended. That's fine. So do you recognize this lady? I guess you should. That's Michelle from the Resistance, and she used to start every conversation by saying, "I shall say this only once." I think it's really a great way to start talking about processing messages once. Another good quote that I found on the web is from Matthias, a person who I respect greatly because whatever he says, it's really insightful, and he says that in this distributed world, there are two hard problems. And I'm not going to touch the message ordering problem. I'm going to focus solely on the message delivery problem today. So why is that so difficult? It should be simple, right? Delivering a message once should be as simple as this. It's a simple algorithm. Check if I have already delivered the message. If not, then deliver the message, process the message, and then mark it as delivered and done, right? Should be as simple as that. The problem, though, is that in distributed systems, things get distributed. And if you distribute that algorithm between two processes, failure can occur. Failure can occur both when transferring the message from the infrastructure to the application, and they can also occur when transferring the acknowledgement. Yes, I have processed the message from the application to the infrastructure, a message queue or any messaging infrastructure. If we map this process, check, mark, and process in this way, then we have failures here in between. And this situation is quite well known by theoretical computer scientists. That's a two generals problem. Who remembers two generals problem? Couple of hands raised. So should be simple, right? If my engineering problem maps to a well-known computer science problem, then somebody probably have solved it before. So let me tell you a bit about the two generals problem. I think you have some mountains in Ireland. Sean told me about some. So here's the situation. There is a city. Somebody, not smart enough, put a city in the valley. And there are two generals in two valleys, on the left and on the right. In this case, though, it happened to be beneficial for the city because in order for those generals to conquer the city, they need to attack at the same time. They need to coordinate because otherwise, if one of them attacks the city, he will be defeated. So they need to sync. And in order to do so, they can only send messengers between them because the mountains here and here prevent line of sight. The problem is that when a messenger goes from one general to the other, it can get killed here because the guards watch for messengers. And it has been proven, and I want to quote the whole proof here, that this problem cannot be solved without having an infinite amount of messengers. With finite amount of messengers, you cannot have an agreement between those two. A simplified proof is that you can never be sure if your messenger that tells the other guy to attack in 2 weeks' time has gone through or has been killed when going to the other general or coming back. So we don't know if the other guy received your message. So when 2 days pass and you need to decide to attack, you have still the dilemma, should I attack or not? So unfortunately, computer scientists proved that it's not possible. The only thing we can do, though, as engineers, is shift the problem around. That's what we do for a living, right, as software engineers. So if we have this check, process, mark algorithm, as simple as that, moved to the application itself, then the problem is a bit different. It's not a problem of exactly once message delivery. It's a problem of exactly once processing. The infrastructure will happily deliver the message to our application multiple times, as many times as it is necessary, but the application will take care of processing it only once. And because application controls its state, it can make sure that the check if process, and mark steps are executed in the same transaction atomically. So there are no failures possible between those steps. If I have a data store that has atomic transactions, then I can manage it, and it's not a distributed problem anymore. So to quote Matthias again, I think technically you can get exactly once processing, but never exactly once delivery. Exactly once delivery is a distributed problem, not solvable. Exactly once processing is a local problem. And actually, exactly once processing is all about how you manage your state in the application. So the state needs to include both the business state and the message processing state. And those requirements are enough to achieve exactly once message processing within our application. And it also, well, when I created this slide, I realized that it's really boils down to a great paper from 1981, which is called End-to-End Argument. And it boils down to you can do whatever, well, you can do smart things in all the layers in a computer stack. But in the end, if you want reliability, you need to guarantee the reliability of communication at the top on the application layer. All the layers below, those can provide, well, they can provide for better throughput or better, they can provide some heuristics, but in the end, it's up to the application layer to guarantee it. So enough with theory, let's get to practice. And we will be practicing cooking pierogi. And I figured it out because I watched a couple of presentations about Swiss cheese or Swiss chocolate and Swedish meatballs. So I figured I'll do something related to it. So imagine there's a startup, a Polish startup that wants to disrupt the global pierogi delivery market. We want to deliver them everywhere in the world, and we want to be the best. And there is a team of smart engineers, designers, marketing people, everybody is on board, and they want to do it. So the engineers come together, and they want to figure out the architecture for the system. And it has to be scalable, right? When you are a startup, you don't want to rewrite it every year. You obviously will get 1 million customers after the first 7 days. So you want to be scalable. How you do it? You scale your front ends, right? You can have multiple front ends. You want to have multiple backend things and a queue in between because you want to be reactive and you want to be async, all the funny buzzwords you have. And now, because we are on a microservices meetup, you don't have a monolithic backend. You have lots of many small backend things. Every backend thing has its own queue to make things more complex. And everything is asynchronous. That's the simplest architecture they could come up with. And in the meantime, the UX designers figure out that that's the MVP UI. So it's a page. You can create an order. And what you can do here is you can add various types of pierogi with mushrooms, with meat, whatever. There's one limitation because it's an MVP. You can only add one item of each type. Right? You can add, you can remove, you cannot edit, and you can add one item of each type. So the engineers looked at their architecture, and they figured that they have a problem. Because of their nicely decoupled architecture, front ends and back ends, they need to send messages around, like add item to a shopping cart. And those messages can get duplicated because of some network conditions or whatever. Messages do get duplicated on the wire. And now they don't want to deliver twice as many pierogi, or they don't want to charge the customer twice. So they need to figure out how to do it. Unfortunately, that kind of UI is really designed to solve that kind of problem. So the UX designers, well, created a UI that not only looks good, but is easy to implement. Why is it so easy? Because those engineers figured out that this order is a set, right? Every item is unique, and you don't have duplicates. That's a set. And a set has very nice properties. Set operations, at least some of them, are idempotent. We frequently use term idempotent when we actually need, when we mean message deduplication or some stuff, but like real idempotence is a mathematical term. It's a property of a function. That means that if a function is idempotent, if applied twice, is the same as if it was applied once. A set operation such as set union is idempotent operation. So, well, let's use this. Let me switch to a demo mode. Here's the application that they created. I used the. Okay, so what they first think before building the real UI, that just built a console application, and second thing, they read that chaos monkeys are good. So what they did is they created a chaos monkey that duplicates every message sent by every service, just to ensure that their application behaves correctly. So let me add some order. I'm not typing here. Okay, what just happened is the message got duplicated on the wire, and it was processed. And then, when the duplicate came, what you can see here is immediate retry is going to retry message blah 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 because of primary key violation, and it cannot insert the duplicate key because we assign order IDs on the client side. When our submit order command was duplicated, the database detected the primary key violation and prevented creating two orders. That's fine. That was easy part. Now let's add some stuff. Did it work? Or did I misspell something? Excuse me for a second. Oh, it did work. Okay, so what happened is I tried to add some pierogi to my order. And again, first message was processed correctly. The second one was rejected. And what it says is the violation of primary key constraint. And the important item, is it here? The important item is not here. That's because that's not this demo. I'm sorry for the failure. I hit the wrong button. Okay, that's what I wanted to achieve. So the important stuff is here, if you can see it. The key is 0 ABC. That means that the key to the order item is the actual properties of an order item. 0 is the type, and ABC is the order ID. So I cannot insert more than one item for a given order with a given type. That's what was expected. Now let's try something else. Let's add some Swiss cheese. And well, if you were Polish, you would know that it's not a valid thing for pierogi.
You misspelled that.
Thanks. Okay, and what you can see is an error here saying that, well, I cannot add this. That's fine. The problem, though, is here. I told you about the microservices architecture and multiple services. So this backend service, it publishes an event, item added. And this poor downstream service processes those events. And if you can see here, the item added meat, that's fine. But what you can see here is not really okay. So this service got an event that Swiss cheese type of filling was added, which is not true because we just rejected that command with an error and didn't store that in a database. So what happens is, well, with this kind of architecture, it's not immediately, it's not eventually consistent architecture due to a queue. It's immediately inconsistent because this downstream system sees a state that is not really, that has not happened, that state change was prevented. So it's not a great solution. But let's see a code, and I'm sure you are not all C# developers, but that's fine because it's not really a super complex C# code. So those two annotations here say that I require a unique index in a database, and this unique index has, well, its function is to enforce the set semantics of my order. And then there's a pretty easy code that checks if item of this same type has already been added. If not, then I add it, and then I publish a message. And then after publishing a message, after publishing a message, I save changes to a database. And that's really the source of the problem. As you can see here, the ordering problem. I first publish the message, and then I attempt to store the changes in the database, the state. If the new state of the object is rejected, then I'll already publish a message. And that's the problem with Swiss cheese that you have been observing. And that problem has a name. It's a ghost message. It's a ghost message because it doesn't really relate to any state change that happened. And there is a simple solution to ghost message problem. To prevent ghosts, you just switch the order. So instead of publishing and then persisting, you persist and publish. First, I need to persist the state, my state, make sure that I really did persist it to the database of some sort, and then publish my messages. There is one problem though with that, or one challenge. If I fail some midway through here, then I don't know if I published. So if I get a duplicate message, I need to republish. But we'll get back to that situation in a moment. So the team was pretty much successful. The sales were quite good. So they held a retrospective about the problem that they were facing. And they figured out that the message deduplication problem that they thought they are dealing with is not the actual problem. So let me try to frame the problem with them. We want the outcome to be the same no matter how many times we receive and process the message. That's the idempotence part. But there's the other part of it. We don't want to leak any information to other systems or other services in our architecture if we haven't actually processed a message, if we rejected the message. So we don't want the ghost messages. Two parts of the problem. So we want to be to really do stuff or entirely or not. We want the messages to be published when a database state changes. So the sales were really good, as you can see, as in every successful startup. And then the product manager came to the engineer room and said, well, if you could just add quantity to the order lines, that would be great. That's easy, right? The UX people said that, well, that's just one another column in a user interface and we'll be happy. So they added the quantity column. And, well, from their point of view, job is done. Now the problem for the engineers is though, well, with that new column, the order is no longer a set. The items are no longer uniquely defined by the type. I can add, for example, 3 pierogi with meat, and then I can add another item with 7 pierogi with meat, and that's completely fine with this user interaction. So, well, what do we do? How do we deduplicate our messages? But there were smart engineers, and they figured it out. So what they figured is that in this new design, although that's not a set, the order items are still immutable. So you can add them, but there is no edit button. They didn't know if the UX guys forgot about it or it was intentional, but there is no edit button. So there can be, the items can be either created or removed, but not edited. The nice thing about that is that there can be only one message associated with an order item, right? The one that created the order item. Then the order item can be deleted, but that's also fine, because creating stuff and deleting stuff is idempotent. I can create the same order item multiple times, it's created. I can delete it multiple times, and then it's deleted. It cannot be more deleted than just deleted. So, well, they went to their computers and they created something. And this something is the thing that I showed you before. So that's why the confusion. I have 4 demos, and I started with demo number 2. So let me again submit an order with the same ID and add something to it. Come on. Processing. Okay. The zoom thing doesn't work as I expected. Okay, so we got an error as expected because the message got duplicate, but now the error is different. I cannot insert duplicate key in object order lines. Duplicate is free CA blah blah blah. And it's not a random GUID, it's the same value as we see here as a message ID. So what they did is every message has an ID that uniquely identifies it. If a message is a duplicate, there are 2 copies of a message that have the same ID. So if I take the message ID and I stick it as a key, as an ID of the order line, then I can, creating an order line, I can detect if the same order line has already been created. So what they did is they included the message processing state, they baked it in the application state by using the same IDs. And it solved their problem. It also solved the problem of ghost messages. So if I add Swiss cheese, yeah, then we should see a nice error here. Yep, and nothing really happened in the downstream system. So the downstream system team is super happy. Well, not really. So what happened here is they received only the meet added order event, and that's fine. The problem though is if you look at those IDs here, they are different. So they got a meet item added event, 2 copies of it with different IDs. Now how do they deduplicate that? From the downstream system perspective, that those are just 2 messages, and they are different. So the downstream system, it thinks that actually 2 items were added, not 1. So it's still immediately inconsistent. The problem is that when we introduce the ghost messages fix, when we swap the publish with persist operators, we introduce this republishing. As you can see here, as you will be able to see in a second, what it says is a duplicate or partially failed item message detected, republishing. And when I'm republishing, I generate a new ID, right? So I published an event. I failed the processing, so I restarted. I'm republishing, brand new GUID, and that's the problem. When we republish events in that kind of situation, we better have a consistent IDs. We better have deterministic IDs, because otherwise somebody else receiving those messages won't be able to deduplicate them. If I open the code, the changes are pretty minor. So the ID is now a string that is assigned, and it's assigned from the message ID. So if I check if there is an order line that has an ID matching with the message ID, and if not, I'm just creating it. And bear with me. And now the order is changed. As you can see, first I save the changes to the database, and then I publish. That's why I created this republishing problem. Well, they have created it. So the situation is like this. There are 3 endpoints with microservices. There might be 30. The first one the chaos monkey duplicates the message with ID 1 to 3. This thing processes this and deduplicates, and that's fine. But when it republishes, when there's failure, it republishes the same message with different ID. Solution: generate message IDs in a deterministic manner. Well, it's a solution. I wouldn't say it's a good solution, because how do you generate deterministically message IDs? Well, there are a couple of options, like you can hash a message body, like a Git hashes commits, but then two commands that have the same meaning would hash to same value, which is probably incorrect. You can generate it based on the incoming message ID. There are different strategies, but there is no silver bullet for that, no winning strategy. But nevertheless, they were again successful, and the sales were pretty good. So again, the product manager comes in and says, well, if you could allow order lines to be modified, updated, that would be great. And again, from the user interface perspective, that's just like a thingy text box here, and you can edit it and click update, and it's all fine. But it's not. From the development perspective, the situation changed completely, because now you can have a series of messages associated with each item. You can have one message, one command that created an item, and then you can have as many as you want messages that update that order item, and then you can have it deleted. Bottom line is you can have multiple messages associated with an item. And what the implementation team discovered is that it's not a unique situation here. It's common in their microservices architecture that there are multiple messages coming into the same aggregate roots or entities, and they need to deal with that situation somehow. So let's see how they dealt with it. Let me close this one and fire up this third demo and do the same thing as usual. Okay, and let's observe what happened. Okay, again, error message, again, violation of primary key constraint, but as you can see here, the constraint is on a different table. We haven't seen that table before. It's table processed messages. What is this thing? Let me open my SQL console and select star from it. Sorry for typing one hand. From. Yeah, SQL is hard. Okay, that's a single column containing two IDs. So what's happening here is that when I process a message in the same transaction as I persist my application state, I store a tiny little thing in that processed messages table, which is a message ID. And then I know that I processed that message, and when a copy of that message comes again, I know that I have processed it and I don't need to reprocess that. As you can see also here, the team managed to solve the problem of a non-deterministic IDs. I'll show you in a second how they did that, but as you can see, both copies of that event have the same ID. Let me close this window and open up this one and see the code. So first, the infrastructure. The nice thing that they managed to do is they managed to decouple the infrastructure from the business to some degree. So what they created is a behavior. It's a like filter in pipes and filters, or an OIN infrastructure. It's a thing that is executed before the message handler. So a message comes in, this thing gets executed and passes control over to the handler. That's a piece of infrastructure, and what it does is it checks if there is a processed message record for that message. If it's not null, if there is one, then we set this flag. We will use that flag later. Processed equals true. If there is no process message record, we just add it to our unit of work to be added later to the database. And we pass the call context over to the handler. So let's see what the handler does in turn. What it does is it checks that processed flag. And only if the message has not been yet processed, it executes the business logic here. Because we want to execute that once, when the message has not been processed before. And then it does the publishing of messages. So what it does is, if the message comes there for the first time, the process flag is set to false. I execute my business logic, add the order item, and publish the event. If another copy of that message is processed, I skip the whole part because process is set to true, and I republish the message. And here is the fix to the duplication problem in a downstream system. So I set my message ID to the next message ID value. And what is that next message ID? I will show you, but I need to scroll it. So the team created this magic GUID utility thing that creates deterministic GUIDs. How? So what they figured out is that they can create a new GUID based on the old GUID by just hashing it. So they take the bytes, they hash them again, and they create a new ID. Seems to be a good solution. But what they discovered in their testing environment is that some messages disappear. So there is one system, another system, and in that first system, it receives randomly messages either from one system or the other, but not two of them at the same time. The problem was a diamond problem. So there was one service that published an event. Then in the second layer, there were two services that subscribed to that event and published their own events in turn. And then there was this poor fourth system that subscribed to those two events. And because they were just hashing the incoming GUID, the two events that the fourth system received, there were the same values. So they were considered the same event, even though they had different types and different values. So what they figured out that they will add a name of the microservice or name of the queue to that hashing function to enforce some kind of uniqueness. That saved the day for them. And to sum up what they did so far was that they actually implemented this check, process, mark algorithm, right? They created a piece of infrastructure that stores their message IDs, has some function to check if the message has been processed, and the message handler is pretty much decoupled from that infrastructure, despite that its processed flag looks more readable than previously, and it can be reused in various services. So to summarize, they tried idempotency, they tried of different kinds. They ended up with check, process, mark algorithm because of the changes in their data model or the interaction with the user that they have. But that's not the end of the story, and that's not the end of my time. So a manager comes back in and says that sales were again super high, and we have some spare time. We want to boost the morale of the team. So he says, if you could just refrain from adding new features for a month or two and just make the code cleaner and more readable. That doesn't happen really often, right? Well, it doesn't happen ever, but it happened from the team. It's a fairy tale of mine, so let's pretend it happened. So what one guy on the team thought was that, well, they use a messaging framework, so they can, if they have this free time, they can just contact the developers and maybe they will get some hints. So he hits that chat with our developers button, and he sees this thing. So a guy called Szymon Pobiega says, hi, how can I help you? Well, we do that sometimes. And the developer says, hi there, are there any established patterns for implementing idempotent message handlers? And the guy on the other side responds, have you tried the outbox? So here's the pattern that we use for automatic deduplication. I wouldn't say idempotence. That's development of the thing that this pierogi team has implemented. And let me walk you through that diagram. So first thing, this green thing on the top is a transport transaction. It begins with receiving a message from a queue and ends with committing that received transaction. So before that happens here, the message is not removed from the queue. The application gets the message, it has some time to process it, and then it actually removes it from the queue, confirms the transaction. If this last thing doesn't happen, the message goes back to the queue and somebody else can receive it, some other thread. So what happens? Let me walk you through the happy path. We receive the message and we check in a database, have we processed that message? The same stuff as previously in that pierogi system. If no, let's walk the happy path. If we haven't seen that message before, then the outbox transaction starts. And that's a transaction that spans both the business data and the message processing data. They have to be in the same kind of storage. So within that outbox transaction, there is a handler. So business logic executes here, and that business logic can send messages, store data, send messages in any order. But it's not that easy. The sending messages is not actually sending. We get those messages that we pretend to send them, and we store them in a buffer. And then when everything is done, we store those messages in a database. So this is the step that, that's a workaround for the deterministic message generation problem. We figured that deterministic message generation is very business sensitive. How you generate the message IDs in a deterministic manner, it really depends on the business model, on the architecture. But what you can do, instead of generating them deterministically each time, is you can store them, and then they are deterministic because they are persisted. So when we persist them, we commit that transaction. And at that point, all the processing is done, all the messages are ready to be sent. So then we dispatch them to the actual queue. So we start talking to a queue, like RabbitMQ or whatever kind of queue, and we send the messages one by one to that queue. And after we are done with sending those messages, in a separate transaction, we mark that message record as processed or as dispatched. And only after that, we commit the original transaction. So if we failed some midway through before that commit, the message goes back to the queue. So let me walk you through some failure scenarios. Like we can fail here, and that's safe. We haven't modified any state up until now. We cannot fail here because that's a transaction, so we can fail here. If we fail here, our message goes back to the queue, comes up again, we check the state, and we see, oh, we have that transaction because we stored. We know that message, we know that it has been processed, and we know that outgoing messages that resulted from that processing. So we happily skip that thing and go to dispatch directly. Then we can have another failure condition. We can fail after dispatching. And that's also fine, because we come back again, we see that message has been processed. Those are the outgoing messages that resulted, so we dispatch them again. Yes, in that case, we dispatch again, even though they were dispatched, but we cannot tell the truth. When we fail in this step, we cannot distinguish if we actually dispatched or not. And last but not least, we mark the message as dispatched. If we fail here, then that's the easy part, because we did all the work. We created a record with messages, we dispatched them, and we mark this record as dispatched, so we are done. So when we check here, we can tell that everything is done, we can skip that message. And that last step is quite important because we have issues in the past with not having them. So what we would do is we wouldn't really change anything in a mark as dispatch. So we processed the whole message, we failed in the last step, and when we come back again, when the message comes back again, we dispatch again. And this, well, it's a minor change. It doesn't affect the correctness of the application, but the problem is that a single duplicate message will result in pushing out duplicate messages to the downstream systems. So you have one duplicate, then you have two duplicates, then you have four, and so on. And we kill rabbit brokers quite easily with that thing if you have like 8 layers of microservices in the architecture. So it's kind of essential to mark the message as dispatched and not redispatch if we actually confirmed that we did this job. So let me maybe quickly run through the demo as we have some more time. So we have a bit different error here. The table name is now outbox data, not processed messages as before. And we won't select star from it. What we can do is we can take a look at the code. And now it's only the business code that matters. The infrastructure is done by the framework. And that business code doesn't even mention any deduplication stuff. It doesn't really have to depend on any processed flag because it's all done by the algorithm. So it just purely creates new order line or changes the quantity if one exists. There is no deduplication code happening here. So it's a nice way to package deduplication with that kind of pattern. Now, again, that was all good. A project manager comes back again and says, well, now if you could replace the SQL server with some document store, and I won't be picky on document stores today, but generally, well, I should be more specific here. The thing that I meant here is some cloud-based document store or cloud-based table storage that doesn't have cross-entity transactions. Everything is fine with the patterns that I showed you as long as you can, in a single transaction, persist both business state and message processing state. If you cannot have a transaction that spans 2 documents or 2 entities, then you are out of luck, at least with that pattern. There are different patterns with that, but that's a completely different story. So let me try to summarize. We've seen first, we cannot say you shall say it only once. It's a bad abstraction. Instead, you should mean, well, you should do it only once. That's exactly once processing, not exactly once delivery. And what we've seen here, the team struggled first with natural idempotency with a set-based structures. Then they tried to employ natural idempotency of immutable items. Then they have an explicit model, which included the message ID in the business model. The downside of which was that we have models interleaving each other, and we have concepts coming from infrastructure such as message ID interleaved with business concepts. And then they ended up with an explicit model where they had the processed message table. Last but not least, they had a slightly better algorithm implemented with the framework. There is a couple of problems, though, that are unaddressed still, even with the latest algorithm. So what do you think, how long those deduplication records will be kept? The processed message table, how long we should keep those around? A week, a month, a year? That there is no correct answer, right? You cannot, if you want to be absolutely sure that you deduplicate all the messages, you keep them forever. Because, well, you need to be sure. So those kinds of problems are still funny to solve. And, well, with that, I'd like to thank you for your time, and I'll be around here and in the pub so we can chat. Thank you.